The core thing that we're going to use in this course to describe the way things react with each other, the core mechanic, the core language, the symbolic language that we're going to use, is the curved arrow formalism. Now that you're starting to generate resonance structures, you're going to be using these curved arrows as electronic bookkeeping, showing where the electrons go. And as we move away from resonance and into the actual reactions for the rest of the course, you're going to continue to use this. If you move on to organic 2, you're going to use this absolutely everywhere. If you take biochemistry, anything like that, this is the standard way of depicting what happens in an organic mechanism. Organic chemists are interested in the movement of electrons. Atoms happen to be along for the ride, or not, as the case may be, but we're fundamentally about the movement of electrons. So what we're always doing with the curved arrows, and they're usually drawn that way, with a end and a head, a tail and a head, is they're showing the movement of electrons. And this is as opposed to atoms. Atoms may or may not move, but the electronic arrows show the movement of electrons and not atoms. So what I did on the first day was illustrate the key to organic chemistry. A nucleophile will always attack an electrophile. This nucleophile will end up making a bond there. Well, that was a fancy term, and I was making a point there. But the key idea is a nucleophile is a place that has too much electron density. So basically, lots of electrons will go ahead and share those electrons with a place that needs electrons. So something that has a lot of electron density, like a nucleophile, will go ahead and push those electrons to a place that needs electron density, like an electrophile. And the way you show that happening is with a curved arrow. And the arrow is always going to start where the electrons are, and it's always going to go to where the electrons end up. In other words, you're always going to either start with a lone pair or a bond. You simply cannot start anywhere else. That's because a lone pair is a pair of electrons, and that can be where it starts, and a bond is also a place where electrons exist. It's a pair of electrons between two atoms. So you can either start at a lone pair or at a bond, and that will be where it goes. You don't have to start fundamentally at a place that has a minus, but having a place with at least some delta minus would be good. Having a full-on minus would be even better. So here, the nucleophile has too much electron density, that's why it's going to share some, but the arrow itself is going to start at the lone pair and then go. And then where do electrons end up? Well, they will always end up wherever they eventually come to rest, and that either means you're going to create a bond, and that's what's implied by this particular arrow, or you can potentially create a lone pair, which I've already showed you several examples of in the resonance videos. So this nucleophile is fundamentally creating a bond between itself and the electrophile. So in other words, what will end up being the result of the arrow that I drew above would be as follows. The nucleophile, the atom itself, is still in green. The electrophile, the atom itself, is in blue. And then the bond is the pair of electrons that was green to begin with and now has joined to become a bond between the nucleophile and the electrophile. The result of taking the nucleophile and doing that reaction with it is that you create this new bond. So one of the two typical scenarios is illustrated here, where the lone pair becomes a bond. The other typical scenario would be one given by drawing a resonance structure for, say, an aldehyde, where if I were to draw the second best resonance structure for this aldehyde, what I would do is I would start where electrons are, in other words, one of these two double bond, and then I would go to form a lone pair on the oxygen to end to create a lone pair. So the key idea being that it moves to become a lone pair, therefore these red electrons were the ones that were originally a bond here, and everything else remains unchanged. And now we end up with charge because this carbon ends up lacking an octet, and this oxygen ends up with an additional pair of electrons, therefore has too much electron density. So the key thing to keep in mind as you are generating Lewis structures, resonance structures, is the curved arrow formalism is all about showing the movement of electrons and not atoms. Therefore, it always needs to start where electrons are, either as a lone pair or as a bond. Ideally in a place that has extra electron density like this, but not necessarily. Here, the double bond, there's extra electron density because it's a double bond, but there is no actual charge there. But the arrow also needs to either create a bond in the end, like here, to make a new bond, or it must end up as a lone pair on one of the atoms, like this oxygen. The double bond becomes a lone pair on the oxygen. One more key rule is that you really can't skip get too far away. What I've shown you so far is that this pair of electrons belongs either to this carbon or to this oxygen. So I'm allowed to shove it up onto the oxygen. I'm also allowed to shove it down there, but I can't fly it somewhere else in the molecule. With the exception that it is possible to take a pair of electrons and react with something that's somewhere else, and do a reaction across two different molecules. But you can't slide it around wherever you want within a molecule. But that ends up being an issue that we will address later. For now, the thing that I care most about is you're showing movement of electrons, not atoms. You start either at a lone pair or a bond, and you end by either creating a bond or a lone pair. And usually what's going to happen is if you start as a lone pair, you're going to create a bond with the arrow, but if you start with a bond, then it's going to end up creating a lone pair eventually. Usually you're sort of sliding back and forth between those thoughts. This is the way you generate good resonance structures. And once you're comfortable with resonance structures and start doing reactions, this will be the formalism that you use to describe reactions as well.